Okay, so it's our great pleasure to have Eric Chitambar from University of Illinois at Urbana-Champaign. Eric is a long-time collaborator of myself, and he knows basically everyone in our center for a long, long time. So it's a very good friend, in my opinion. And then today, Eric would talk about his very recent result about how to build multiple access channel in with just a single particle. So the floor is yours. Go ahead.
Great. Thank you, Min-Hsiu. And it's nice to be, I'd normally say it's nice to be visiting everyone again, but I guess we make the most of the situation. So I just finished my dinner here, so I'm going to treat this as an after dinner talk, which means that I hope you will stop me at any point, ask questions, and hopefully this will stimulate some discussion. So I'm going to have my thumbnails minimized, but so I might not, if you like raise your hand or you do something, just speak up, just interrupt me, please. Okay, so what I want to talk about tonight is some work that I've done with two of my students, Yuji and Shinan. Actually, Yuji is technically not my student. He's a student of my colleague who's an experimentalist. So Yuji comes with an experimental group, but he's also a very good theorist. And Shinan has just joined my group at University of Illinois in PhD program. So this is some previous work we've done, and we also have some ongoing work as well. Okay, so let me start by just motivating the topic. It actually came from two papers, I guess now about 3 years old or over 3 years old. And this was some work by Del Santo and Dakic, where they showed this communication setup where they were able to achieve two-way communication with a single quantum particle. So they identify sort of a very basic advantage that in communication when you're using a quantum versus a classical particle. And I kind of want to sketch out their protocol here because it really lays the foundation for some of the work that we did. So the idea is that you have Alice and Bob separated, and there's some particle source that's distributed to both of them. And A and B are their inputs. So just imagine they want to send 0, 1 information. Then they do some encoding on this particle that they receive. They send it through a channel, and then they make some measurement at the end. So if you start off with an entangled state where you can think of 0 as being a path, 0 indicating that it's a vacuum, 1 indicating that you have a particle along the particular path. So you start off with a path superposition state. And then they do an encoding, which is just a sigma z based on whether their message is 0 or 1. And then this channel here is essentially a Hadamard rotation in this path basis here. And then at the end, they make a measurement. And because they have these classical side channels, let me see. Can you guys see my pointer at all?
Yes.
Yeah, probably. Yeah, right? Okay. So these classical side channels are crucial for them because basically you can work through it. And what happens is that because they have the side information, Bob can learn Alice's bit A and Alice can learn Bob's bit B. So in using just this single particle that was distributed coherently between the two paths, they have been able to achieve this two-way communication, which classically is not possible. Okay. So this framework actually has appeared a few times in some different settings. So the first is that, at least that I found it in sort of a communication or information theoretic sense, is for the task of quantum fingerprinting. So here we've kind of merged the detectors into one party, which we identify as a referee. And the goal is for the referee to decide whether Alice and Bob are sending the same signals. And so you can think of these as their fingerprints, where they're choosing A or B, and the goal is not necessarily to decode whether the value is A or B, but the goal is to decide whether they're matching. Okay, and so in this case, you can think of this particle as being like a static quantum resource that's used in the task. And so if we wanted to compare it to a classical resource, the static resource would be shared randomness between Alice and Bob. All right, and it's not too easy, it's not too difficult to show just by modifying the previous protocol that I described, that if you do fingerprinting with one classical particle, there'll be an error probability of 1/2, meaning that the referee will make an error in concluding whether A equals B. Whereas with binary fingerprinting, with a quantum particle, there's 0 error. So it's just kind of the same idea repackaged in a different task. And a third iteration of this is maybe more familiar to those coming from a physics background, is just the double-slit experiment. And so here you just think about Alice and Bob that are controlling the slits. So they either open or close the path. And again, we can ask what are sort of the statistics, the measurement statistics in this. And so if we start off with some superposition of paths, and then there's a transformation here, which is again, just like a Hadamard transformation in the path basis, you can work through the calculation, and the probability of measuring 0 is just given by this amplitude here, where you can interpret this amplitude x as the probability of measuring if Bob blocks the path, meaning that the particle has gone through here, and y is the probability of a detection if Alice blocks the path, meaning it goes through the second slit. And then this extra term here is like an interference term, and this is so if there's no blocking whatsoever, you're going to get this interference in the measurement. Okay, and so then like the classic take-home message, which you learn in Introduction to Quantum Mechanics, is that the probability of measuring 0 can differ for a classical or quantum particle. And it comes down to this coherence term here, this x times y. All right, so those are 3 instances of how you can see a difference between using just a quantum and a classical particle in somewhat of a communication setting. And we want to push this even further. Rather than just looking at one particular instance, we want to explore this whole space of communication. And so to make the framework a bit more precise, we're just we want to know the power of one particle, ignoring any internal degrees of freedom, like spin or polarization. And we want to do encoding just in relational properties of the particle. So space-time coordinates, how the particle is located as it's moving from the sender to the receiver. Okay, so that's our game plan here. And to make a concrete model that we work with is, we'll just imagine that we're performing some n path interferometer experiment. And this actually was considered by Biswas, Garcia Diaz, and Winter a few years ago in their study of quantum coherence. They also looked at this basic setting of an n-path interferometer as forming a communication channel. And the way that it works is that there are n parties here, so A1, A2, AN, and each party controls a path between the source and the detector. And so then what the party will do is they have some classical data that they want to communicate, A1, A2, AN, and they'll perform some CP-TP map along the path. And that will be their encoding operation. Okay, and all paths will lead to this receiver B, who then performs some big decoding POVM and obtains a value B. All right, and crucially here, no extra degrees of freedom are allowed. So our mantra is one party, one path. So there's no side channel connecting the encoder to the decoder. I mean, this is actually crucial because we want to limit the communication just one particle. So if you allow for side channels, it sort of blows our model up. And what you end up getting then is basically a framework for a multiple axis channel, because you have your classical data here, which is corresponding to the encoding operation, and then you have your measurement outcome B. So with this in hand, then we ask what types of channels can we generate if we use a quantum particle rather than a classical particle here at our source. And well, we need a bit more structure on the problem because in principle, we have to limit the encoding maps that are performed here, these local encoding maps. Because you could imagine that, say, one particle is produced at the source, but then the encoder ends up generating particles locally and sending those particles to the decoder. So the key constraint that we want to maintain is that there's just a single particle that's used throughout this whole process. So to do this, we introduce what we call number preserving operations. And basically these are the full class of maps that can be physically implemented without introducing any additional particles. So to look at this, we'll look at like in the dilation picture. And so the idea is that we allow for some ancilla ports locally. So E1 to E2, EK, these are all environmental or environment systems. And we apply some unitary here, but the key constraint is that this unitary must be number preserving. So if one particle goes in, one particle must go out, but of course it can be distributed coherently across the environment systems and also to the decoder. So if we trace out these environments, you get channels that look like this. And this probably looks familiar to those who maybe have worked with the resource theory of asymmetry before. This actually is a subset of U1 covariant maps. Slightly different though, because here we're enforcing that U acts invariantly on the number space. Okay, and so for one particle, it's not too difficult to show that actually the channels are just amplitude damping channels. Okay, so that means they have this nice form here. Okay, good. So this is now the rules of the game. So you start off with some state here, and it has support on the single particle subspace. And then each of the encoding maps must be an NP operation, means it must be generated in this particular way. And then there's just some arbitrary decoding POVM at the end. All right, and then we ask what are the channels we can get with these restrictions in place. So we consider all the channels that you can build, and we call these n local maps. And so we'll use this QNAB to denote that full set. And so likewise, what you can do is you could say, well, let's suppose we want to fix the particle, and then we can ask what are all the channels that we can build once we've fixed our particle state. And so this gives us then sort of a refined set of channels. So here, this is A is your input set, B is your output set, and then rho is the state you're using as your particle source. Okay, let me just pause and ask if there are questions at the moment before we look into the classical channels. All right, so far so good then. Okay, so we have these
maybe the only comment, maybe that.
Yeah, please.
Notationally, NP may be a bit confusing to be number preserving, because you'll think of it as NP hard.
Yeah, good. So there, in the context of this talk, there will be no complexity discussions whatsoever. So we'll avoid that ambiguity. But yeah, I agree. Maybe I could use the number sign for number and then NP.
What you mean, like sharp P?
Yeah, sharp P or hashtag P or whatever.
Isn't that also a complexity class?
Yes. Yeah. Okay. All right, guys, you got me. Good. Okay. So now let's ask what happens if we were to send a classical particle through here. All right. So by classical, what we mean is that it's incoherent in the number basis, right? So you can think of this the EIs here. This is just a computational basis state, and there's no coherence between the different paths. So like 1 in AI means that path AI receives 1 particle, and all the other particles are receiving 0, right? So we're basically just, you can think of it this way. We're dealing with classical particles, so think of this like a basketball or a golf ball or something. You flip a coin, and then it tells you which path to send that golf ball down. Okay, and so the encoding strategy is actually very simple here. What happens is that if the ball is sent along path I, then either, I mean, there's really not much you can do. The party can either block the particle, or let it go through. So this QI is the probability that party I lets the ball through when it's sent down his or her path, and then party QI 0 given AI is the probability of blocking, right? Okay, and then the decoding is also easy. Classically, there's not much to it. The decoder just looks at all the end paths and sees whether there's a particle in it or not. So then there's some channel that it performs that we call B here, and this is just the decoding channel. So this would be the probability of outputting B given that a particle is found in path I. That's what that denotes.
Eric, one question. So this probability, is it like the overlap with whatever is the state that is after the maps have acted? Like
this D here?
No, the QI EI AI. So is it just the wave function overlap between EI and?
Honestly, no. Don't think wave function, because here we're just talking about classical particles. So just think about it this way. So AI is the input. Ultimately, each party has some message that they want to send to Bob. So AI is the particular value that wants to get sent to the decoder. So given that particular inputs, this is the probability that they let the particle go through. And this is the probability that they block it.
I see. Okay.
Yeah. Okay, so we paste everything together, and then what we get are channels that look like this. So you can see PI, this is the distribution over the path. And then QI are the local encoders. And then D is the decoder at the end. Okay, so this forms a family of MACs, which we call n-local classical. Okay, so we can soup this up a little bit. We can consider if we allow for shared randomness between the source and the detector. So one way to think about this is that the decoder knows which path the particle was sent. All right, and this encompasses like quantum non-local games, where you could think of the decoder is actually sending the particle to the different parties to do some local operation, and then they send it back to the decoder, or the referee in that case. And now, if we write out the channels that are the classical channels that you form in this model, they look like this, and you can see that it looks very similar to what we just wrote down on the previous slide, right here. Except there's the crucial difference that there's this index I, which means that the decoder knows which path the particle went down. Okay, so this is now a richer family of channels. And so we'll denote this family by C prime. We can go further, and we can say, well, let's let the encoders also have access to this shared randomness. And here the channels now take this particular structure. But actually, this is just now the convex hull of the first set that we discussed. Now you basically are distributing randomness to all the encoders and the decoders, so it's just the convex hull of the local max. Okay, so here's the 3 models. And the relationships is that they form this chain of inclusion. And actually, we can define one more set here, which we call to be separable max. And this has a very convenient mathematical form where it's just a convex combination of one center channels. So here this GI only depends on the input from one of the senders. And so you're basically just averaging over all of these. And the channels of this form include all the other classes that we introduced. All right, so one of our results in the paper is to separate these different models and actually show in some cases they're the same. So for instance, if the output is binary, then they all collapse and the classes are equivalent. If you have binary inputs, so these are n parties, meaning they each encode, they're each sending 0, 1 messages, then you get this set of inclusions. You get a separation between the classical and its convex hull. So in this case, what ends up happening is that you have the convex set, the classical set, local set is non-convex. And then if you have arbitrary A and B, then you get full separation between all these. And I mean, maybe you might guess that you get some of these to collapse, given that you're sending one particle. So if your message set is limited to 0, 1 information, then that might be enough to cover like the whole space of channels. And in fact, that's why you get this full equality here. Okay, so what I want to do for the rest of the talk.
Excuse me, Eric.
Yeah, go ahead.
Could you go back? Yes. So what is the GI again? This separable.
This GI is just arbitrary. So it's if we can decompose our channel in this form, where GI is just some arbitrary channel.
Ah, I see. Okay.
Right. So I mean, it's just saying that the GI only depends on the input from party I.
Okay. Good.
Okay. All right. So what I want to do, pretty much for maybe the rest of the talk, is to discuss this the polytope a little more. And so first, let's return to this double-slit experiment idea that was like on the second or third slide. So I wrote down this term that you can think of the real part of this product. You can express it in this form here. And if we want to remove or put this probabilistic interpretation to it, you can interpret each of these terms in the sum here in terms of a conditional probability. And again, this P0 given 1, 0, this is the probability of measuring 0 if the second block path is blocked. And this would be if the first path is blocked. So 0 is like a blocking. Actually, sorry, that's a typo. These need to be switched. 1 is blocking. So 0 is letting the particle go through, and 1 is blocking. Yeah, because this is neither blocking. And then if you interpret it in this way, then you get almost for free that P0 given 1, 1 should be 0, because if 1 is blocking and both parties block the path, then you shouldn't get any particle going through. So this is always going to be 0. So you can tack this on, and what you get is this particular linear combination of probability values. And this is a well-known quantity known as the I2 coherence. So this has precedence for being studied in quantum optics for a while now, not in the context that we're considering it, but this particular linear combination is well known. And so what we do is we first generalize this I2. So this was for 2 input, 2 output. And now we can do a similar generalization where this is basically considering any 2 parties. We look at this particular linear combination for any set of outputs. And okay, so that's how we define it. I mean, the main take-home point is that this functional suffices to characterize the separable max. So a result is that the MAC has this particular decomposition if and only if each of these second order coherences vanish for any 2 pairs of parties. So this is kind of a nice result because it's very easy to check this, right? You basically just look at the second order coherence for any pair and for any output. And if it all vanishes, then you know that you can construct a decomposition like this.
Eric,
Yeah.
So is this I2 quantity connected to the path entanglement somehow?
Yes, yes it is. So hold that, maybe, I think it's next. Yeah, next slide, you'll see how it is. Okay, and so then what I showed, or what I promised you guys, I just told you, something we found was that for binary outputs, we had all those different families of channels collapse. So we have this equality here. And so then this implies that a binary output multiple axis channel can be simulated with a single classical particle if and only if it has vanishing second order coherences. So not only are you guaranteed that it has this separable decomposition, but you're also given a physical implementation of using just a single classical particle to build this channel. Okay, and now to Madhoff's question, so what about for quantum particles? Okay, so this notation, I know I'm kind of throwing a lot of notation here, but if you recall what this means, this is the family of Macs that can be built using this given state rho. And what we can do is we can look at all the I2 values that you can build using this rho here. And so first thing you can show is that this quantity, this I2 tilde, this turns out to be a monotone under these NP or star hashtag P or whatever we want to call them. Under these free operations in our theory here, this is a monotone, which is good. So it indicates that we're getting, it's giving us something physical, or it's telling us that we're onto something as far as a communication resource. And in fact, what you can show is that the I2, sorry, this should be a tilde here. This tilde is actually given by the amplitude of the off-diagonal term between the I and J party of the matrix rho. So those who have worked on coherence will recognize this right away as being like the L1 measure of coherence for a 2x2 density matrix. And so that's exactly what you do. So here you have n parties, and you basically look at the 2x2 submatrix corresponding to party I and party J. And then you just look at the off-diagonal term, and this gives you exactly the I2. So anytime you have coherence, right, this will be non-zero, which means you're getting a non-classical Mac. Okay, and in fact, you can achieve this. So this I2 value can be achieved using this particular encoding strategy here. So the take-home message is that every coherent state can generate a multiple axis channel outside this classical set here. And it's nice, I think one thing that was kind of pleasant to see is that it gives this L1 coherence kind of an operational meaning, which there's other examples known where you have a similar interpretation of that L1 coherence. Here's just another form of it. Okay, so the next thing we consider is to move beyond just the n-party local channels and consider strategies where you group parties together. Right, so before you look at this definition, look at this picture here. And so you remember the mantra that I said, one party, one path. So now we want to relax that. And now we want to group different paths together, and we allow some joint encoding like this. Okay, and so for any integer between 1 and n, say k, then we fix the number of parties that we allow to jointly encode. And then we build the channels up like that. So basically this GS, this object here, what this means is that it's a channel defined by subset S. So S is some subset of parties with no more than k parties in it. And you allow the channel to depend on just the inputs from those parties. So you can see this generalizes this here. And then operationally, you can think of this as like encoders working together in groups of size no greater than k. All right, and so then any Mac that's not in this set here, n minus 1, we'll call it genuinely multiple axis channel. So the idea here is if you, there's various definitions of multipartite entanglement, but one notion that has been studied is this genuine multipartite entanglement. And the idea there is that you can't take a density matrix and decompose it into a convex combination of biseparable states. So this is the analog to that in terms of multiple axis channels. You're not able to decompose it into channels that depend on less than n inputs. All right. So this is what we're interested in looking at, or is this class here. So first, as a toy example, let's consider the 3-2 local max. So this 3-2 means that it's 3 parties, 3 senders, 1 receiver, but we're going to allow 2 of them to encode together. Right. So here's what the polytope looks like. So we consider all possible channels that have this form. Notice each of these depend on only two inputs. And so you've worked through it, and actually this polytope is characterized by 1 equality and 4 inequalities. Meaning that if it has this, if P has this particular decomposition, then it must satisfy this equality here. All right, and this kind of looks arbitrary at first, but again, this has precedence of being studied in the literature because it's a quantity known as third order coherence. Okay, so what is third order coherence? So let's go back to the double slit, and now let's add a third slit. Okay, so now we have 3 slits here, and now we prepare some initial superposition across the 3 different paths. And again, you do just like a generalized Hadamard on these guys, and then you measure. And so you can interpret this 0, 1, 1. Remember, 1 is if again, I goofed it. 1 is if there's paths are blocked. So you get this amplitude squared, and you can decompose it into different terms. So this would be if Alice opens and Bob opens and Charlie blocks, this would be Alice opens, Charlie opens, and Bob blocks, etc. And yeah, so then this last one comes in for free again. And what this whole term here, all these terms here sum up to give us this I3 quantity that I identify here. Okay. And so it turns out that if you work through it, that actually this I3 this linear combination vanishes. Even if you start off with a quantum particle here in a superposition of these different paths, this equality will always be satisfied. So so the reason this is interesting is it's kind of like a no-go for quantum theory, meaning that even quantum mechanics is not able to generate a non-zero I3 value. So for I2 it can, and we saw that it's a generic property. You can generate this. You can generate non-zero I2, but for I3 you're not able to. And the reason actually has to do with the fact it goes back to Born's rule, and the fact that you're computing these probabilities by amplitude squared. And this I3 is somehow capturing like a cubic feature. And so there's been some work, I didn't give the reference here, but in our paper, we reference just some work done on like GPTs where they consider theories that allow for non-zero I3. Or you could impose this as a constraint, as a relaxation to quantum mechanics, and say you want to study some GPT where you require I3 to be 0. What sort of theory does that give you? So I bring this up now just because there's much interest in studying this I3, and so we found another connection here in terms of these multiple axis channels.
So Eric.
Yeah.
So how about higher order, like I4 and?
Yeah, right.
above?
They all vanish.
0?
Yes.
Okay.
Yeah. Okay. So going back to where we stumbled upon this. So this came from this polytope, this 3-2. And I told you that it's characterized by 1 equality and 4 inequalities. So if we're trying to find a quantum violation, we can't look at the equality, but we can try to look at the inequalities. And so here are the 4 inequalities, and this is the one we're going to be interested in. because it looks something like a fingerprinting inequality, now generalized to 3 parties. And fingerprinting, because it has the feature that when 2 parties have matching fingerprints, like here in the first term, the second and third party have the same inputs, then the output should be 0. So, so when 2 parties have matching fingerprints, the output should be the fingerprint of the third party. That's the structure of this particular inequality here. Okay, so our question is, can we violate this with some quantum encoding? And in fact, you can violate it. And here's another interesting connection, that it's related to something which is known as the coherence rank of your density matrix. So let me just introduce or review this concept here. So for a density matrix rho, its coherence rank is, it means that the supportive rho can't be spanned by vectors with coherence rank less than d. So you have a d level genuine coherence if you can't represent the density matrix as a convex combination of pure states with coherence rank less than d. And the coherence rank of a state is just the number of non-zero terms when you write it out in your incoherent basis. So here the I here would be the paths, right? So we were thinking about n different paths we can send our particle. And so we're interested then in the number of non-zero terms that we have in our superposition here, and that's defining the rank of psi. Okay, so we have this rho across three paths, and we're interested in the coherence rank of this state rho. And some prior work that was done by Martin Ringbauer and Kohlhardt was actually quantifying the 3-level coherence of a Q-trit state. And so the way you can do this is you introduce what's known as the companion matrix. So if here's rho is your density matrix, companion matrix is defined as this. And a nice feature here is that if you have a pure state, you can demand that the elements are all real here. So then the companion matrix just takes this nice form where we remove the absolute values. And our observation was, well, if you look at this, you can actually interpret this companion matrix in terms of an encoding strategy. So you can write it out as 3 encoding maps performed, and then minus this extra term here, where the encoding map is just a phase encoding. And so this is just like sigma z. Okay, and so then what that allows you to do is you can express this fingerprinting inequality in terms of the companion matrix. And what you get is you get this expression here. So it's the norm of the companion matrix plus 2. And if you remember what the fingerprinting inequality says, that this sum should be bounded by 3. So then we get our theorem here that every 3-party pure state violates the fingerprinting equality if and only if it has coherence rank 3. Because then we applied this theorem by Martin Ringbauer and co-authors that the norm of this would be greater than 1. So that would give us a violation of our fingerprinting inequality. Okay, and then we just compute some examples of this. All right, so take-home message. That you can do more with less non-locality in the following sense. So here these 3 are like your classical max, and we're allowing joint encoding on 2 of the channels, and you're taking some convex combination of them. But the point is, with a quantum particle, you can do things that you can't do on the left-hand side if you impose the locality here. All right, so the quantum particle, one way to think about this is that you're using the coherence of the quantum particle to simulate genuine encoding across all 3 paths with a classical particle. Okay. Then, like the last result I want to discuss is if we wanted to scale this up to more paths. And so we can use this technique of lifting inequalities, which is known in studying Bell inequalities. And the idea is that if you know you have a valid facet of a polytope for certain dimension or certain number of parties, and you want to generalize that to more parties, you can use this idea of lifting. And so here's the lifted version of that fingerprinting inequality. And so our first result was actually proving that this indeed is a valid facet of this now n-party set of channels. So these are all binary input, binary output. And so a result that was independently shown by Horvath and Dakic was that we can always violate this inequality, this generalized fingerprinting equality, using an n-party local quantum map. So again, the notation, this n-1 means that we're allowing n-1 of the paths to encode together. And there are certain NACs you can generate if you, with a quantum particle, where you still enforce the locality between each of the parties. All right, and so basically, our violation, though, is not so impressive. Well, okay, I mean, it's interesting, but it scales like 1 over n cubed. So if you want to try to demonstrate this experimentally, it can be a bit challenging. We have, as I mentioned at the very beginning, Yuji, who's co-author of this paper, comes from the experimental group, and so our plan is to do some sort of experiment here, but it does make it challenging because these quantum violations are actually small comparatively. Okay, sorry. One more result. So everything so far I've been discussing has been in terms of these facet inequalities and violating inequalities. But I wanted to motivate this as like a communication advantage. And so to flesh that out, once you look at a more operational quantity for communication purposes, and so here for multiple axis channel, the natural quantifier would be the rate region of your two senders. So recalling a result from a very classic result in classical information theory. So if you want to identify the achievable rate region of a multiple axis channel, it's just characterized by the three mutual information terms that are optimized over all product distribution inputs. So we can say, all right, fine. So we have these channels, or we have these different classes of multiple axis channels. What sort of rate regions do they generate? So first, it's fairly easy to see that if you have one classical particle, your rate region just looks like this. And so you're basically one bit of communication for each sender, and then it's just the convex hull of that. But for the quantum max, you get something that's more interesting. Here you get something that's non-convex, and the non-convexity is because we're not assuming that there's shared randomness between the decoder and the encoders. So we're just looking here at the most simple, or the most basic scenario of just a single particle source, and then you do the local encoding and then the POVM decoding. And so you're in fact able to achieve a larger rate region using a quantum particle. And I think one thing that surprised us was that actually, so this dark line here, you might not be able to read in the key here, but the dark line is the rate achieved with a maximally coherent state, or a uniform superposition of paths. But what surprised us is that you can actually do a bit better if you break the symmetry and you work with some asymmetric superposition. And I should say, I mean, when I'm claiming this, so this is all done with very careful numerical analysis, but I don't claim to have a rigorous proof that's of this bound here. But we did work very hard numerically to get it as close as we could to identifying this rate region here. Okay, so I'm going to wrap up with just some comments here. So first, again, the motivation of our this project was to unify single particle classical and quantum experiments under this operational framework, similar in spirit to a resource theory where we identify our free operations and we ask what we can accomplish with those operations. So here our free operations were these number preserving maps. And what this leads us to are communication channels that go beyond phase discrimination games. So the general framework here was considered to, in terms of phase discrimination games before, where the local paths, the end paths of an interferometer were controlled by performing phase shifts. And then it was the channels that emerged with these phase shifts were studied by these series of papers here. We take that one step further and move beyond the phase discrimination and consider full channel discrimination. Okay, so some future work that we're working on right now is to understand these NP operations a bit better. And most of our results were based on this either blocking the path or doing a 0 pi phase encoding. And in fact, in some cases, we've been able to prove that the 0 pi phase encoding is optimal. But in other cases, it's still open. And so again, we want to further refine this distinction between the two classical and quantum maps in terms of these rate regions. So we have some other results in that direction. And so everything here is cast in terms of one particle. Of course, the next question would be, well, what if we have more than one particle? And this is a good question. It's something we'll look into. And one thing to point out, though, is that if we want to do this carefully, then we need to start thinking it in terms of differentiating between boson and fermions here. It'll generate different statistics. If it's just one particle, then the difference is, there is no difference between the two species. So that makes it a more challenging endeavor, but it also makes it perhaps more exciting as well. So with that, I thank you, and I am happy to discuss more.
Very much. Do we have any questions?
Yeah, Eric, I had a question.
Mm-hmm.
So
Yeah.
Regarding the rate region where you said that the maximum is not achieved by the completely coherent state, the maximally coherent state, sorry.
Yeah.
So do you know what kind of state is actually getting?
Yeah, I do. I didn't write it down because, again, this was done numerically, so it's rather messy. But I think it's like so the weight is it's like 45% on one path and 55% on the other. But it's, you know, it's not, we have just some numerical value.
Yeah, it seems very strange because your system is completely symmetrical on both sides, right?
Yeah, no, it surprised us as well. I mean, I think one thing is that the encoding operations are not symmetric. So even in the case of the uniform superposition state, to get your different rate points here, you need to use asymmetric encoding, which I mean is that one party encodes their 0-1 information using one family of maps, and the other party encodes 0-1 information using another family of maps. And somehow the reason why the asymmetry is helpful here is because think about it from the decoder's perspective. The decoder is trying to resolve the two messages that are coming in, right? And so if each party is doing the same thing, it makes it difficult to differentiate which message is being sent from which party. So somehow the asymmetry is actually helping on the decoding process.
Right, right. So another question I had was that...
Before you just move on to the next question, is that in any way related to, in Bell violations, there's something, I can't quite remember the name of the author, but my understanding is that these kind of optimal technique for establishing absolute security is to not use maximally entangled state. Is this in any way related, do you think?
It could be.
I'm just trying to remember the context.
Okay, so maybe a result that you're thinking of or that comes to mind when you describe that is that you, like this, the I3322 inequality, which is like three choices of measurement and two on each party. So the maximal violation there is not a maximally entangled state. And so there, yeah, I guess if you want to think of it.
I think the one I'm thinking of is the Eberhard inequality, I think it is.
Okay.
And I can't quite remember it's been a while since I've thought about this, so I can't quite remember, but my memory is that it's, I mean, it's not that it's, they go for like an imbalanced entangled state or something, I think. And and I can't remember whether it's overcoming, like to overcome something like decoy state attacks or something. I'm not sure whether.
I see.
Oh well, it'd be interesting to know if there's because I mean, if you've got some sort of imbalanced asymmetric state, it seems like there are other contexts where such states prove to be somehow more optimal than the symmetric state.
Yeah, I mean, it's a good point. I'll think about that some more. But yeah, thanks for pointing the comment.
So the second question I had was, is there any way of, like, when you're thinking about extending this to more particles, and is there any connection to boson sampling at some point? Because you have a bunch of, like, there you have multiple outputs and multiple inputs, but.
Yeah, I mean, I guess that would sort of be included in this framework, because you could think of it as a communication channel. Yeah, my short answer would be yes, you could do it. But the tricky thing though is that you really want to, at least our motivation was to differentiate the classical and the quantum scenarios. And so I would want to first turn and say, well, if we're going to introduce more particles, what are the classical bounds in this case? And so now the classical strategy is it's not as simple as just blocking or not blocking, right? You could imagine a scenario where like, yeah, I mean, maybe there's more possibilities that could emerge. For instance, like maybe you could have something where one party like absorbs the particle and the other party releases one or something. Yeah, you just got to be, that would be my reason for thinking that it's slightly different than just pure boson sampling, because you really want to flesh out the classical bounds.
Do we have any questions? So I actually have just one quick question. So you restrict to the number preserving encoding strategy, right? What about anything beyond that operations? Or have you ever thought about like generalizing encoding as well?
Yeah. Well, okay, but we haven't thought of it. But you could do something more. I mean, you could do all. I mentioned that these encoding operations were a subset of the U1 covariance operations, and so you could allow for just U1 encoding, U1 covariant maps, and that would give you. Well, okay, I don't know. This is one thing we considered. I should have listed as an open problem, is to see whether the channels would differ if you allow for that particular family of maps. The qubits, for one particle, we know it won't. We were able to show that actually, if you consider the convex hull of our maps, it actually includes all U1 covariant maps. So, but beyond that, yeah, you could consider other relaxations, and it would just give you another set of channels.
And what is your classical, is there any constraint on the classical encoding strategies? I cannot, you probably mentioned that.
Yeah, I mean, the classical encoding strategies are also NP. Just in diagonal basis. So what that turns out to be is just either blocking or not blocking.
Okay.
So I mean, you can imagine that you're trying to communicate to me a yes/no answer, and if you don't send me a particle, then I know your answer is no. If you do send me a particle, the answer is yes.
So
yeah.
So maybe a tricky situation would also maybe exist is when if you enlarge the encoding strategy on both the classical case or in quantum case, the advantage might disappear, right?
Yeah.
Yeah. Okay.
Right. Yeah. Exactly. So that's why I think this going to more particles. That would be one way you could enlarge both of them, and maybe you only get this on the single particle level.
Okay.
You don't know, or having some other relaxation.
Okay. Good. Very good. Do we have any further questions? Okay, so if not, let's give Eric another Prof. Thank you.
Good, thanks guys. It was fun, and I hope to visit, I don't know when, but hopefully soon.
Good, good, you are always welcome.